They had to come up with an idea or concept, and they
Yes.
passed that concept on to the Dutch and South African students.
Yeah.
And then they worked on it for a couple hours. So the Indonesians worked on it first for like 3-4 hours to
Yeah.
come up with an idea, and then they passed it on to the Dutch and the South Africans, and then they passed it on to the Canadians, and we collaborated with the
Okay.
St. Lawrence College students.
Oh,
And
excellent.
then we had to
Yeah.
finalize a prototype of a game they had to develop on SDG or more specifically EDI.
Oh, that's great. Yeah.
So, and then our students had to finalize whatever they got from the other students
Yeah.
into almost like a pitch of what does the game look like.
Nice.
I should build a prototype and actually do a final pitch.
How are the ideas? Like, was
I
it?
don't know. I haven't looked at it.
Oh
yet.
yeah, you
But
got
what I
a
saw
recording.
was
Yeah,
really,
yeah,
really
great.
cool.
Yeah.
Like games for like on coffee mugs.
Yes,
To,
yes.
To teach people more about EDI and stuff like that. And there was almost like a crossword puzzle kind of idea.
Yeah.
Somebody came up with like kind of like Monopoly kind of games, but then all the fields changed to different. So it was really there was
Yeah.
some really creative ideas in there.
Well, you've been doing quite a bit of that, right?
Yeah,
Well,
yeah.
so it's
I'm
good.
running
Yeah.
4 different coils
Good.
this semester.
Oh, terrific.
So
Well, maybe at the end of the semester, we have some more time. I'd love to see some of them.
Yeah.
Just to like see a few clips or something.
100%.
Talk about it. But
100%.
okay. Anyways, I got to get
You
set
go do
up.
your class,
See,
all right?
yeah. Have a good day. Yeah.
You too, eh? I
Okay.
hope they fix it.
Yeah. Well, I got to work around. I always have a workaround. Okay.
You will manage.
I'll manage. Hey, Shanti. So, Shanti, I'm just doing a workaround today with the setup here. Can you hear me clearly? Let's see what's comes up on the live chat. Okay, good. Okay. Shanti, on the screen right now, of course, you see me in the classroom sitting on the couch. Do you see a window um, on me that says stop the recording to save it? Do you actually see that at your end? You shouldn't, because I want to leave it open at my end. No, great. Okay, good. So that means I can leave this up here and make sure I have the recording. Okay, good. So I think this is going to work. And Beiruz, can you do me a favor and just sit in that right where, just next to where your coat is, and then we'll get more students. I just want to check and see. Good, that'll work. Yeah. Okay. Anyway, you can sit back there, and I'll get the other students to sit in here. Okay, good. So, and we have the recording going, and so everything will be done off my laptop. So let me get the big board set up here, okay? And Shanti, actually, did we not want to speak privately at some point? I know we had been emailing back and forth. So why don't we, would you let me know in an email at the end of today's class if you would like to speak with me privately about anything, okay? Anyways, I'm going to go to the podium and get set up. Great. Okay. Yeah, we're doing it this way today. The tech is still an issue here, but so we'll be okay. I'm going to run it off this way. So I'm going to go folder. So I'll go here, and I'll go here, and I'll go here. Right. Okay, so let's see what happens when I put this up here. Good, good, good. Okay. So we can still use the board. And in terms of the screens, okay. Nice. So that might just work. First, let's send it, screen share, and wire it. So let's see if we actually get a full thing going here, which would mean, and then that would be, are we going to get it? It sometimes takes a minute or a few seconds. Are we going to get that today? Maybe not. Okay, so that's not. Maybe it's because I hit the wrong thing. So we'll try it again. Okay. Let's see. We want to try export, screen share, wired. Okay. Are we going to get that? Come on in. Jake.
For names was up already.
Okay, let's see. Are we going to get Okay, so that's not. There's a reason for that? Okay, because I've just been a day of tech issues so much. Maybe it's here. Maybe it's here. Yeah, good. Good, I can do it. I can troubleshoot. Okay, nice. Nice. So that's from last week. We're going to clear that away. And actually, we can get two going. So we're going to make all of these 1, 2, and 4. So this is going to be local. This is going to be local, right? Yeah. And we'll go over here. And we'll do. Now, let's send this export, screen share, wired. And so that would mean that if I press it there, we will get that. And will we? Yes, we will. Excellent. Okay. So that's going to work. That is absolutely going to work. And then for the fourth one, we're going to go over here and see if this is going to work. I think we can do it. We can make this happen. First, we need to export it to screen share. We need to go wired, and then we need to do that. And we'll bring this back from last week. Yeah, we'll leave that up here for now. Okay. So I'm just getting the big board set up here. Hi, Cosmos. And let's see if this is a little test. Yes. Excellent. Okay, so that's going to work, which means that I can come back to here and operate it this way. Okay, so we're going to do this, and whoops, yeah, we don't want that. We want to go to the folder, so don't save. We're out of here, and we'll go to DC Connect, and we'll bring in the folder, and that way we can actually get the video going. And it should work. So we have a nice, good, all working, stay, yep, and then we go to Humanities Destiny. Excellent. And then we go into class 9 to get our material. Okay. Now, let's see how this works with audio. Will we get audio? Yes, we will. Nice. And we're going to loop this. And we do by left clicking. Left click, loop it, check it, loop. Okay. Excellent. We can lower that. Nice. Okay. So this is all working. As you can see, this is how it's going to be today, folks, in the Cosmos. And there's some reverb. Is there?
Hello.
Hello. Hi, who's that?
It's me.
Oh, it's Manish. How are you,
The
Manish?
movie goober.
Good.
So
Uh,
I'm sorry I haven't been able to attend class.
Okay. You're my seat. I know, I'm sorry, but I have to host from here, so come sit beside me and you can get some of my great brain
Some of your aura,
waves.
What happened?
Brain waves coming to Andrew. Not that you need them, Andrew, but So everybody, people are coming in right now, and everything is going to work like this today. So
Just for today?
just for today.
Oh, what happened yesterday? I didn't see anything on the
Oh,
YouTube.
I've been troubleshooting like crazy in the last week because I don't have Maureen anymore. Unfortunately, there are
Oh, what happened?
financial constraints at the college,
Oh, uh-oh. That's
cutbacks.
sad.
Yeah, this is the time we live in. However,
I don't like financial constraints. It's stupid.
yeah, I know, but
Because it hurts people more than it.
it's true. But we sometimes have to just work with what we've got, Manish. That's the way
That
it
is
is.
true.
And today started with me popping buttons on my shirt at home, so I knew things were going to start to go from bad to worse, and they have. But
Hey,
anyways,
I'm sorry I'm not there
that's okay.
because I've been doing I've been going in and out of a hospital because my mom's like really sick.
Oh, well, I hope she's going to get better soon.
Yeah. I hate arthritis. It's like the worst.
Well, anyways,
They do that to people.
yeah.
Well, I'm gonna mute because
Okay.
I'm not really
Yeah,
in any
go ahead,
place to
mute, and
talk
I'm going to
much.
just get everything else set up, okay? Just be aware that what we're watching right now is a video on the big board here, Manish, and it's in your folder, Class 9 folder on DC Connect, and it's called Scale of the Universe. Okay, so go ahead and watch that on your own. And for
Got
all,
you.
yeah, and for the rest of you as well, let me just see here if I can do this. And we'll have it kind of like that. No, that may not work too well. So we'll just leave it like this for now. Okay. So for the rest of you in the cosmos, go ahead and click on Scale of the Universe. And of course, mute your microphones as well. I'd like you to watch that before the class begins, okay? All right. So we have a plan. Let me get this ready, the board for everybody. And here we go. And we'll get back on the course soon. So, humanity's destiny today, we just changed dates, and that's basically it. We can change that to afterwards. Maybe not. Maybe we'll leave that for now. I have an idea. We don't want to say, we don't want to. Oh, I lost it. Okay. That's par for the course today. So things are going wrong, but it's all right. We can deal with it. Okay. So we'll do that, and then we'll call this humanity's destiny. Oops. Somebody's got green here. Let's go black back. Good. Okay. Then let's do black back. Humanities Testing Wednesday, March the 12th on board. Wednesday, March 12th. So there you go. You can put your go on board up there. And we'll get that going.
When I type something, I have a set option, right? Like here, let me show you an example. Okay, it's possible that type the same way, usually. For everything else, everything is that type yourself an hour. For some reason, this one here,
Me here. My notebook.
So it's supposed to be right here in R20%. So if
And then we need a pencil too. So let's bring the notebook back.
I can see
Let's bring the pencil back. Let's bring the rest. I even.
just get that.
Yeah. Okay. Okay.
Yeah, scale of the universe.
Great. Scale of the universe. There's some books. And I'm gonna lower this.
That's the main thing.
Okay, let me come back here for a second.
It's not supposed to be like that. So you watch a video?
Actually, I'm gonna bring something else in for a moment. And it's the other video. Okay, just a second.
That's good. So you can record it. Good.
Okay,
That's just.
yeah, hold on. Just gonna come. Open that up a little bit. Great.
It's going to down.
Okay, let me grab a seat here. And oh, look at this bad stain there. Okay. This is how it's going to go. Welcome, everyone, to Humanity's Destiny on Wednesday, March the 12th. And I will get to the onboard group in a moment. We'll do that. As long as we have all the names up there by the end of the class, we're good. I can check with attendance. If there's a problem with audio for the Cosmos, would you please let me know? Just put it in the live chat that you can't hear. But this microphone on the laptop is going to have to pick up everybody in the room. We may have to come a little closer. And most of the time, I'm going to be talking this way, so you may not always hear me clearly. But let me know, okay? As you can see, the tech is continuing to be a problem in this room, and I'm working as best I can to continue having the classes that we have, but just know that the college is facing financial constraints right now, and I have lost Mayreen for tech support, and also regular tech support is not always available. So right now, this is the best we can do. There's a cable that's missing. It should be here, and that's why I can't be fully connected. But this is good enough. At least we can get the recording and we can have a discussion. And I can also lecture from here, and we can get notes together. So we're going to start, okay? And essentially, what we're going to be doing today is we're going to continue to look at this whole idea of new worlds. And this requires something quite maybe new for all of you, which is this idea of cosmic scale, larger planetary scale that allows you to begin to stretch your mind and open your mind up to a much bigger view so that you can mentally be able to deal with the reality of space travel or space exploration. And some have said that in order for us to be able to go into space and continue to remain human in the best way, we almost need a new mind for this. Some have talked about this idea of the coming of the new mind. And that mind is a mind that is able to deal with a much larger reality, essentially. That your reality is not just on the planet, it also includes outer space. And that's a mental kind of development that we need to make in order to be able to remain sort of in control, if you will, and be able to understand what kinds of opportunities we can take advantage of. It's new out there. There is a new kind of reality that humans are increasingly having to face. So what I'd like to do today is establish some really critical facts facts that are stunning, facts that are real, facts that will help you to understand more and more how to think of this sort of larger scale. And the big question that I'm sort of going to be addressing is this idea of what is the totality of our existence? What is the totality? And what I showed you at the beginning was a video, just a little sampling of it called Scale of the Universe. Have any of you seen that video before? Scale of the Universe? No? Okay. Anybody online? Anybody seen the video there? Just park it in the live chat. But you have that video as well as one other video.
Yep.
Oh, go ahead. Yes? Is that somebody online?
I've already watched the video.
Okay. Before the class?
Yeah.
Excellent. And that is that Manish?
Yes. Yes.
Way to go. Okay. So, not a lot of people in the class have seen the video, and that's good. That means I have something that might help you to open your mind. There's another video that I also want to start the class with today that is even more impressive. It comes from the Massachusetts Institute of Technology, MIT, and we have it teed up right now, and I'm going to run it shortly for all of you. And you will see in the Class 9 folder a video called Illustrious, a simulation. And when I tell you online, please watch it so we can be watching it at the same time as the group here. But this is going to help you to understand something about thinking in more totality terms, cosmic terms. For those of you who have been in my short history of the world class, like Barak, you probably will recognize this video. Um, it is one of the most impressive videos that I do show in the global classroom because it's a work of great scholarship by scientists, astronomers, cosmologists, and data scientists at MIT who have essentially recreated as best they can what the Big Bang looked like. So, well, yes and no. So let me just check for a moment with the folks online. Okay, good. Nicholas, you've watched a few other videos from that YouTuber, not this one though.
Yes.
Okay, good. Well, actually, Nicholas, if you could do us a favor and if you have a chance, could you just put in a link or two of the others who have the other videos that you've seen from that YouTuber? Because I think they're brothers, Gary and something Wang, and it's a lovely video that really gives us a sense of scale. So let's stop for a second because I want to just make sure everybody understands where we're heading today before we look at the video. Right now, I have it teed up at the first frame called "To Compute the Laws of Nature." To compute the laws of nature. We live in a time when we have science that allows us to process so much data that we can start to see things, at least simulations, more clearly about the natural world than we ever have. And in a moment, you're going to see something that you have never really seen, which is how it all began, at least how we think it all began, based on the best science today, 13.7 billion years ago. So, first, does anybody have any questions? Anything they'd like to bring to the class's attention before we begin this little journey today into opening your mind to cosmic scale? And then we can start to look at where we think the new worlds are going to be. What might be the next discoveries that humans are going to make in space, and what that will mean for humanity. Any questions? You good, Jake? Yep, go ahead, Andrew. Everything good?
I was asking, when it comes to space exploration,
Yes.
right? Who should we as in the masses put our trust into the government led space exploration or private, like say SpaceX or Blue Origin, or the government, NASA, and I think is ESA.
Well, I think that probably the answer to that, the best answer is both, because both are working together now. For example, SpaceX, Elon Musk's company, which has built the largest rocket ship that humans have built, uh, works closely with NASA as well. He rents out technology to them, and so they work together. The idea of space exploration and space travel is hugely expensive, Andrew, still, and because of that, even the private sector requires cooperation with the public sector too. So if you look at SpaceX, for example, you will see a long-standing relationship that they've had with NASA in terms of collaborating. They're not just on their own. And you see space agencies, the Canadian Space Agency, European Space Agency, of course, the American Space Agency, NASA, and others collaborating. However, it's a good question because we're starting to see political divisions play out in space, not so much in business, but in politics, with China developing its own space program, with the United Arab Emirates, for example, developing its own and not necessarily collaborating with others. And I think going forwards, the real struggle is going to be ensuring that we don't take the same political divisions we have here on Earth into space. So, for the moment, the collaboration is essential. And as a matter of fact, I would just say finally, because Andrew asked a very good question, whether you like it or not, the relationship between the American president and Elon Musk is a fascinating case study in our future in terms of space. You see government and you see business working very closely together. I'm going to put aside this whole idea of conflict of interest. Elon Musk was never elected for anything. But what you see on a daily basis now is government and business working together in a very powerful way. And we might see more of that happen in other countries in the future. But ethically, Andrew, and morally, this is a huge question on how can business be working so closely. Elon, literally, you have Donald Trump showing off Tesla cars as he did yesterday. And who's going to benefit from that? Elon Musk. He's going to make a lot more money. So it's highly suspect in terms of that part. But it tells you something about the need for collaboration to do big things in space. And Donald Trump has made it very clear he wants to go to Mars. Well, that too. Unfortunately, we have to deal with this beast called the MAGA movement and Donald Trump. It is a beast. We have to deal with it. So, good question from Andrew. And unless I see any other questions here, Yukta.
I have a question.
Sure.
I have already mentioned in last week's discussion post that even if we move there, how will we survive there with like all the planets have their different gravity and air pressures which are not meant to be for us?
Well,
Because right now when astronauts go there, they wear particular space suits.
sure.
So how will we survive there if we are not able to wear them all the day?
Well, I think that's a very good question. If you can, to note this down, because I'm going to be asking you in a moment, as probably teams of, we have 3 screens working, so it would be probably, teams of 2 and 3, to list out critical facts that you can find from your research. And that might be one fact, which is not just ideas, but facts. So the question you would want answered is, what do we need to know about what we're learning in our research now to adapt to this? So you would go to a space agency, could be the Canadian Space Agency or American, and try to find an important fact that speaks to what we're doing about this. And it might be something like, We are in the process of developing a certain kind of spacesuit. NASA is developing. I'm making this up for the moment. But I want you to find facts that can speak to critical questions you have. And you may find something that really speaks to our ability to adjust in terms of spacesuit, in terms of physical training that we have to do, in terms of psychological training, in terms of the kinds of tools that we want to take with us into space. That's called a payload. When a spacecraft goes into space, it takes stuff with it. That's called its payload. And SpaceX is making trips routinely now into space with payloads. More satellites up into space or even to the moon. So maybe there's a certain kind of payload that has to be taken that's going to allow us to adjust better. Okay? I will say one thing to Yukta's question about adapting. I have mentioned this before, but let me just reiterate. Humans have the most capable tools mentally and physically to adapt to new environments. We've been doing that for thousands of years in our evolution, Yukta, from the hunter-gatherers and foragers that we were 10, 15,000 years ago. Humans know how to adapt.
Yeah, but it's more than adaptability, right? Because we are not just adapting the cold or hot weather or something. I'm talking about the air pressure of that planet, which is like if that pressure is more or less than my body, then my veins and everything burst out.
Okay, I think Yukta's really, I want to put her to work immediately, okay? So today I'm trying to do things a little differently to make it work with all of this. I want you to go over to that second screen, and leave up the Mars, just swipe all the way to an empty slide, okay? And I would like you to write down, as best you can, the question that you would like to answer that you just gave to us, okay? So, exactly. So Yukta, everybody is swiping, and these notes will be available to all of you, of course, in the folder after class. So go ahead, and while we're continuing the discussion, go ahead, and we can see it up on the big board. What exactly is the question you're asking? Just go ahead and write it, okay? Cosmic scale. Larger planet-wide solar system scale that enables us to deal with problems at that scale. So let's start, okay? And I'm going to go around, and we have Andrew, we have Burak, Beiruz, and David. David's here, and Jake. And we have Yukta, who's on the board already. Unfortunately, you can't see the big board because of the tech issues today, but we will tell you what's there, and we will work with this. Now, let's start with Andrew. We'll go here, and then we'll go around. Andrew, just off the top of your head, what is the most amazing fact that you can tell us about space, outer space? Just something you know.
That's a fact
Yeah, a fact.
that it is vast and varied. That is a fact.
Okay, vast and very well. It's the beginning of a fact. It's not precise enough. So we want precision today.
Precision.
Yeah, but keep going, because I can help you. But I want yeah.
Well, outer space. And Pluto's once a planet, but no, it's not.
Yes.
Pluto. That was
Yeah,
interesting.
yeah. Pluto.
It used to be a planet.
It used to be a planet. Now it's just a little dwarf planet, right at the edge of our solar system. Okay, so keep going. I really like.
Yeah, it's that that we are just one of many galaxies.
Yes. Okay.
We just one of.
Of how many galaxies?
I think it's maybe countless. I'm not sure if they have an exact figure.
Countless is still not precise enough. Let's try and get some precision. Millions, billions, thousands.
In terms of fact,
Go on. Let's see off the top of your head.
million sounds too much. Let's say thousands. Million sounds too much, but obviously I could be wrong.
Billions.
Of galaxies.
Billions.
Underestimate the size.
We believe that our galaxy, the Milky Way galaxy, is one of billions of galaxies. And in a moment, I'm going to show you a video that gives you an amazing overview of how galaxies get formed as a result of the Big Bang. Billions. Billions. Now, let's try and not make this too difficult, but I'm going to help you a little bit with it. In the video that we were watching, Scale of the Universe, at the beginning, did anybody see in the lower right-hand corner the number 10 to how many particular decimals? So Beirut's, as the scale of the universe was going larger and smaller, the 10 number was changing. When it got to the observable universe,
10 to the power of 27.
10 to the power of 27. 10 to the power of 27. Something like that. I think Beirut is got it. I would check it, but you're very close, and he may be absolutely right. What is 10 to the power of 27 in terms of million, trillion, quadrillion, quintillion? Do you know, it just goes, Andrew, we have to think that, open and stretch to 10 to the power of 27. How many zeros is that? 27 zeros.
Well, 28 because of the 10.
Oh, because of the 10. I could make Yukta's life miserable right now and ask her to write, well, Jake's gone and done it. Okay, there's 10 to how many?
10 to the power of 27.
10 to the power. Could you put that in front of the camera so they can see? There is cosmic scale.
Wow. That requires
It,
expansion.
exactly. That's great, Jake. Thank you. Thank you very much.
Yes.
Okay, so for all of you online, I'm going to go to Barak next, and then Beirut, David, and Jake's already done some good work. You can take a break. In the live chat, go ahead and write down the most stunning fact about outer space off the top of your head. And right now we can say, for Andrew, the fact is that our galaxy, the Milky Way, is one of billions of galaxies in the observable universe. So we're in this realm now, everybody, of 10 to the power of something. And it gets bigger and bigger. And this is real.
10 to the power of infinite.
Well, do you know what Google is? Actually, Google, the name Google, is a particular numerical term. If you actually ask Jake, what is a Google? Google is 10 to the power of something. It might even be 10 to the power of 40 or 50. I'm not sure, but it's huge. So Google itself comes from a numerical term in terms of that scale. And in terms of that scale. Yukta, this is great, okay? Keep going, because I'm going to ask you in a moment to write down some facts together before we actually break into the groups. But I want to go to Barak, because I want to give everybody, at least in the inner circle, a chance to give us one fact. So we have first, the Milky Way galaxy is one of billions, not thousands, which is what Andrew sort of thought. Not millions, but billions. Okay, Barak, go ahead.
So we kind of talked about size already, but I want to kind of expand on that with some, raw data we have. Yeah, I think everybody knows the Voyager. If you're interested in space, we sent 2 probes into the deep soul, the galaxy. At least that's what most people believe.
Yes.
Well, it's just left our solar system. Just. It was sent at the 1970s, and it just left our solar system.
Wow. Excellent.
How many years is this? So.
Well, let's do a little bit of math.
Yeah, let's call it. I think it was the launch of 1977.
It was in the 70s. That's right, the Voyager.
I don't know the exact date. Maybe the 77s, but at least like 50 years. It's just leave our solar system.
Yeah, solar system. Okay.
And we can still receive some data from back with the radio waves because they travel at the speed of light, but now it takes 2 whole days to send one message and get it back. So basically, it's just only one sun day away. We're talking about,
Let's break this down because Burak has given some really good information about cosmic scale. I'm going to ask Yukta first to write down on the big board fact number 1. Okay? Fact number 1. And I just had an idea to ensure that all of you online could see the board. If one of us here in this room joins the video conference and points their phone camera at the board, online, all of you will be able to see what Yukta writes. So, do we need to do that? Is it okay if we just stay with what we have, guys, and we will tell you what's on the board and what Yukta is writing? You can see her sort of behind me, and we can tell you, okay? Fair enough. Okay, so fact number 1. The Milky Way galaxy is one of billions of galaxies. Milky Way, one of billions. We're really going to get our minds blown in a moment because Burak just spoke about a solar system, and that's just one of billions inside one galaxy. So let's just, number 1, the Milky Way galaxy is one of billions of galaxies in the observable universe. Fact number 2. The universe, as far as we know, is 13.7 billion years old. You're going to see that shortly in the video, okay? The universe is 13.7 billion years old. Good. Number 3, let's go to Burak. The fact there, let's pick out one, okay? Think about what you said, and in one nice, clear sentence, Burak, if you can just explain it, what's the fact?
So basically, the Voyager crafts that we made are the fastest things the humanity ever made to this day. And yet, even after 50 years, it only traveled one light day far away from the Earth.
Wow, this is good. We're going to get this, okay? Because there's a lot of... The other thing about thinking cosmically, as we're doing, is this is pure science, pure math. And it's complicated. There's a lot of information, and we have to be able to distill it down so that it's nice and clear. Burak is giving us some great information about the Voyager, which is a planetary probe craft that was dispatched in the 1970s to go to the farthest reaches of outer space, moving at the fastest speed that we humans have created for a spacecraft. And he said that only after 50 years of traveling through space, just 50 years, it's just beginning to reach the outer edges of the solar system.
One of them passed it, the Voyager 2, I think a little bit behind, but it will also pass it, but still didn't pass it.
I'm not entirely sure. I know that the Voyager was approaching the edges of our solar system, and then it would enter another solar system. I wasn't sure if it had passed it yet. But think about this, okay? The fact is, it has taken, fact number 3, it has taken 50 years for humans to reach the edge of our solar system with our best machine. This will tell you something about how big it is and how much there is out there. It has taken 50 years for humans to reach the edge of our solar system with our best machine. That's nothing. That's a drop in the, it's like we haven't even gone into the ocean yet. We're still putting our feet into the water. Think about this, everybody, okay? Our galaxy is called the Milky Way galaxy. A galaxy consists of a collection of stars, billions of stars. Our galaxy, our solar system is just one star. So there are billions of other solar systems out there, and that's just our galaxy, Andrew. Then we have other galaxies in billions, and we are only just in 2025 beginning to reach the edge of just our solar system. That's nothing. This tells you how much there is. And there's another critical fact here. Let's see if you can find this out. What is the fastest spacecraft? What is the fastest rocket ship that we have built as of 2025? How fast can it go? Because speed of the machines we create will dictate what we can see. The Voyager is moving at a very slow speed. It was created in the 1970s. We're now in 2025.
It basically used the slingshot, like use the gravitational pull of the
Others.
planets to slingshot itself to the space, right?
But between the gravitational fields, it's in between stars, it's interstellar. It still needs juice to be able to get into the gravitational fields of other systems. So, again, what you're going to start to appreciate is how little we know, how much there is out there that we have not even touched yet. And this should tell you something about our future. This should tell you something about why there is such a big push in so many parts of the world now to increase their space programs. Because many people want to be the first to see and then extract. But that's another thing in terms of resources and what happens. We've only just begun to reach the edge of one solar system, and here we are in 2025. But let's answer a question, okay? Yukt, are you okay still staying on the notes? Yeah, because you're writing well, and we can always relieve you, but you have nice, clear writing. So, research question. What is the fastest spacecraft or fastest thing that we humans have created as of today that we can travel on? Or something can travel on it. A camera. The Voyager does not have a person. It has cameras, has devices to see things, to probe. So what is the fastest? Let's see. We'll put Jake to work on this, okay? You're working on it? What's that?
Apollo 10.
Apollo 10? Okay, let's see. This is good.
Which is the fastest speed ever traveled by human, which is 39,897 kilometers an hour.
Doesn't Elon Musk's rocket that he just launched go faster than that? Why don't you do this? Elon Musk, just a few weeks ago in the US, with Donald Trump there, his great new buddy, launched what he said is the most powerful rocket that's ever been built, and no one contests that.
So the fastest,
How fast is it?
I'm not sure, but the fastest spacecraft ever built is actually the Parker Solar Probe.
Okay. Parker Solar Probe?
4,300,000 miles an hour.
Okay, let's get this down because this is good. Number 4.
Last year.
The Parker Solar Probe. The Parker Solar Probe is just entering the corona of the sun in the last months. It's a program at NASA that has been ongoing for about 60 years now. And it has taken them this long to be able to finally get this probe into the atmosphere of the sun, to get closer to the sun than any machine ever has. It's called the Parker Solar Probe. How fast is that again?
4,300,000 miles an hour.
Number 5, and we'll stop there. Parker Solar Probe it moves its velocity. It's just entering corona of the sun, and we'll get the velocity down, and then we're going to stop, and I'm going to get you up, and I also want to show you the video. So what's the velocity of the Parker Solar Probe again, Jay?
I know the speed.
What's the speed?
43000.
43000. So how many zeros are there? 43,000, 430,000. So we'll get this down, okay? Yukta's writing this down now. So the speed is
430,000.
430,000 kilometers an hour. Okay, 430,000 kilometers an hour. Well, isn't that interesting?
No, it's miles per hour. That's it's miles per hour. It's km per hour is 692,000.
I don't think it's 430,000, and the reason per hour. Yeah. Per hour. God, because for a moment I thought we were dealing with speed of light. Speed of light is the fastest thing we know of in nature, and it moves at 300 kilometers per second.
This moves at 492 seconds.
No, speed of light. Yes.
This moves at 192.22 kilometers a second.
Great, okay. Parker Solar Probe moves at 192,000 kilometers per second.
No, I said 192.22. I never said 1,000.
So it would be 19,222? Okay.
No,
Okay.
192.22 kilometers a second.
Okay, so yeah, it's 192,000 kilometers per second. That's fine, yeah. It's just, you can put 0.22 or 00. It's 192,000 kilometers per second. Okay. But that's good. Okay, so let's just, and then we're going to stop before it gets, we get really nerdy with numbers. But I love to do this because this is pure science and pure math, and this is the language of space exploration. You have to understand these numbers and get your mind around them. Okay, so the fastest thing we know of in nature, Albert Einstein showed us this with his great work in the early part of the 20th century with his discoveries, and that is first, that the speed of light, which is constant in nature, moves at 300,000 kilometers per second. And Jake has just told us that probably the fastest thing that humans have built as of today in terms of speed moves at 192,000 kilometers per second. That's a spacecraft. It tells you how far we still have to go in order to be moving at the speed that's going to take us a lot further into space. Essentially, the two figures here that are critical, 300,000 kilometers per second is the speed of light. That's nature. Humans have only been able to reach with their machines 192,000 kilometers per second. So that's a little more than half of the speed of light. No, not 2/3. But it's we have a long way to go. And that's really what I want you to sort of sit back and think about now before I show you this video, and then we'll break for a moment. Your future, humanity's destiny, has so much to do with understanding space. Quite a few of you in your discussion posts and in our activity last week felt that we really shouldn't be going to space. There are too many problems on Earth, and we shouldn't be spending this kind of time and money thinking about space. I'm afraid that that's not going to happen. Humans and countries continually want to expand. Humans, especially, are very adventurous. You can't stop that. The problem is politics. The problem is institutions that we create that sometimes don't understand what to do with the fruits of our discoveries. But the human and you, if you really be honest with yourself, all of you here are curious. You want to know. And if somebody tells you you can't go there, you likely will find a way to go there because that's just the way we are. So I want to stop and just remind you about all of this in terms of its relevance for our destiny, but now I want to go back in time. And I want to show you something remarkable that really will help you to understand that even though we humans are just testing the water now with our toes, we've barely entered into this vast expanse of outer space. We're just starting to. The fact is that we have made some critical discoveries already, and we're learning a lot more. And one of the things we have learned in our ever increasing mental horizon is that our religions have not understood creation. Now, if that doesn't get your attention, I'm not sure what will. But for those of you who are religious, you may not like what I'm about to say, but you may want to challenge this. I'm going to show you what science tells us about our origins. It's very cosmic in its scale. We're talking about 13.7 billion years ago. Something happened. Something came out of nothing. But as the Greeks would tell you, the great Greeks and their early philosophy, nothing ever comes out of nothing. We just haven't seen beyond yet 13.7 billion years ago. But 13.7 billion years is what we believe, with our best science, is how it all began, how the universe started, how evolution started. And I'm going to show you how we know that, and I'm going to show you what it looked like. So after that, we'll come back and we're going to have a little more discussion and maybe an activity, and then we're going to end kind of early today so I can deal with all this tech stuff in this classroom, which is such a pain. So for those of you online, please now go watch the illustrious simulation. And I'm going to show it here, and then we will come back in a moment, okay, and talk about this. So guys, here we go. I'm going to show you, you can come and grab a seat, okay, so you can see this. I'm going to turn off the lights, and you can see this in complete, right across here. You can work today, can't you? No. There you go. Oh, here we go. Go ahead. Here we go, folks. The beginning. this up. I just want to read these sources. 'Cause- yeah. So you can see the sources. This is a really well done, accurate, or the best we have. Get this working? There we go.
I'm like a pro with it's up there.
Now, does anybody have any questions on what they just saw in terms of understanding it? And I'd like to spend just a few minutes on this before we start to do some more facts together with pairs or teams, because there's some critical information here that maybe wasn't apparent. How do we determine the age of something? How do we know that this took place over 13.7 billion years? That's number one. And what is all that stuff, gas and dark matter? And why is that important? Well, first, like the first video that we saw today, where we saw the changing decimal power in the lower right-hand corner, this video also had something in the lower right-hand corner that was really important. It's called redshift. Does anybody know what redshift is? This is a very important way of understanding space and how we determine the age of something in space. Light, which is the fastest thing we know of, moves at 300,000 kilometers per second. As it moves through space over time and time and time, it begins to degrade and turn more red. We know that there was some kind of event 13.7 billion years ago that was so bright and so powerful, and its light has been dimming and getting redder and redder over these billions of years. And that's how we can say that that light is so old, because of its redness, the shift in its redness. So we can go back in time and we can begin to understand that there was an event 13.7 billion years ago that was very bright and very hot. And since that time, the heat and the light have been traveling through space, and they have been fading and getting cooler and getting redder at the same time. And that's how we know what is the age of that particular light. The second thing we need to know is everything did not begin with humans. It began with hydrogen and it began with helium. And those gases at the beginning of the Big Bang are exactly what you were seeing begin to evolve and form stars and eventually form other objects. Number one and number two on the periodic table, hydrogen and helium. They are the two most important elements in the universe, and they were there right at the beginning. So you've seen something, just the tip, if you will, of how we begin to open ourselves to a bigger view. Here's what I want to do for the moment. We have 3 screens, and so we have 1, 2, 3, 4, 5, 6. Okay, perfect. Let's put Yukta and Jake on number 1. Go back to number 1, okay? And let's put Andrew and Beiruz on number 2, and Burak and David number 4, okay? And we're going to do a little bit more work together, all right? And I'm going to get all of them set up, and then I will come back to the cosmos, okay? So here you go. First, take this time as well to put your names on number 1, okay, for the onboard. So that's the pen for group 1 group. Make sure you get your names up there, exactly. And then Every group should have a pen. I'm going to come around and get the 3 screens going. And what we need is screen number 4. So we have screen 1. That's good. Excellent. We're doing our onboard. And while onboard is working, I'm going to come over here and get this. Oh, there we go. Okay. So let's do this. Okay, you can start there. There's you. I think Barack or Beirut has the pen. Oh, I know what I need to do. Sorry, Dave. Before this. Okay. You're all ready? Nice. Okay. So let's bring this up and see if it's going to work. Hopefully it will. Yes, it does. So at least this is all working. Okay, so group 1, team 1, team 2, and team 4. And we see all of your notes up here. We started with team 1. And where are Yukta's note? Oh, Yukta's in team 2. Okay, so we'll work with that. That's fine. Here's what I'd like you to do for the next 15 minutes. The same with all of you in the cosmos, okay? So I'm going to give direction from here. I would like each of you to do a little research. You can go to the space agency websites if you need. Please not Wikipedia, but a little bit more precise in terms of from a space agency or from some sort of space organization that is credible. And write down 5 amazing facts about outer space. The most interesting facts, something that speaks to the scale of space exploration and helps us to understand how to think about space. Please go ahead. 5. All right? And the same with all of you, but I'm going to give you a slightly scaled down version of this. For each of you in the live chat, I would like each of you to write 2 of the most impressive facts about space. Go ahead. And you can take your time. We have 15 minutes for this, okay? Excellent. Meanwhile, I'm going to try something with my phone, see if this works. And that would require me to. I could use the camera. No, that might just be a little bit. 5 space facts. Five. Good. So you can see everybody there. Nice. 5. Very possible for more intelligent life to be out there. That's the beginning. That's not a fact. Who? That's very vague. Needs to be more precise. You're on it though. Okay, so Jake, I'll help you, okay? You're saying it's very possible for more intelligent life to be out there.
Like 99% is a guarantee that there's other intelligent or more intelligent.
Who says that?
Research.
What research?
Well, it's the fact that we've only really got, to Mars, right?
Yes.
As the most terraformed body.
Our probe. We have a probe. We have our lunar or our probes up there. Yes.
The conditions for Earth have been met to allow not only humans to thrive, but multiple other species of animals going all the way back to Jurassic and even during the periods before Jurassic. It is also quite very, very, very possible that other conditions have been met similarly in different galaxies, different planets for other life forms to evolve.
You may be right, but we need more precision now. That's not a fact. That's the beginning of a fact. We need something precise.
I'll back you.
Okay, keep going. A fact has to be precise, and it will usually have a number to it that can help us to really think of it specifically. as something more real. Anything can be very possible, Jake, quite honestly.
Possibility of you being killed by a pigeon is it's not. Is it a lot? But it's not zero.
That's true, but there are pigeons that have been congregating at my subway stop in Hyde Park, and they've been getting quite annoying. Okay, so let's see what Alina. I've got to get my glasses to see what's happening in the live chat. So we have so many sources of light in the whole universe.
Isn't it like dark? Consumes the light. Catch. I think that's what it is, right? Oh, that happened. You highlighted it.
You will know if you have a fact if likely there's a number with it, a number that's verifiable. So we know, for example, light moves at 300,000 kilometers per second because that has been proven, it's been confirmed, and it's accepted as commonly as the fact that the sun is hot.
I think it's because it's like our ozone layer.
So let's see. Alina is saying Pluto was long considered a ninth planet, but was classified as okay. That's a fact. My comment on this, Alina, would be: so what? That's interesting, but does it really speak to space in terms of something really amazing that tells us about the size of space, the speed at which things go? Okay, now Laura Lai, only 1 teaspoon of a neutron star weighs the same. Now we're getting somewhere. Laura Lai, where did you get that interesting little piece of information that really begins to blow the mind? Try to blow our minds, Alina, with the next fact that you put in there, okay? This is starting to blow our mind. Only 1 teaspoon of a neutron star weighs the same as the whole human population? Okay. Good. Okay, fair enough. So BBC is your source on it. Lorelei, 2 things. What is a neutron star compared to a star like the sun? Or is the sun a neutron star? I don't believe the sun is a neutron star. I may be wrong. Is the sun a neutron star?
I think it's
No?
I forget
Okay.
the exact term for it, but
Yeah.
it's its own category.
Okay, because Lorelai's got a good source here. BBC Sky at Night. BBC's fine. And what does the whole human population weigh? So if you took 8 billion people on Earth and you put a number to it, what would that number be, Lorelei? Now we get into mind-blowing stuff. And we're into cosmic scale. And in the meantime, Lorelei, if you can find me a button for my shirt, could you bring it to the next class so I can sew my shirt? Thank you. Okay. Good. Okay, so Burak and Beirut and Jake are all working. Neptune has only completed 1 orbit around the sun since its discovery. That's cool. 99% of our solar system's mass is the sun. Yeah, exactly. That's another mind-blowing piece of information. Just how big the sun is. That virtually all the mass in our solar system is the sun. That means the Earth is just a little speck is a little pebble. It's a little grain of sand. And yet on this grain of sand, look at what has happened. Life is formed, all these animals, all these plants, and then we humans in this tiny, tiny little thing. We learn that small things in nature have a lot of power. Small things. tiny things. The quantum, for any of you who really want to get into this stuff, you should get into quantum science, quantum mechanics, the study of tiny things, not big things. That's where a lot of scientific discovery is being made right now, in quantum. Great.
My gamer brain goes,
Jupiter has the most. What's that one? Jupiter has the most.
It has the most moons.
It has the most moons.
Confirmed, yeah.
How many?
95.
95.
Yeah.
Sorry, what has
Wow,
the most
Jupiter. I didn't know it had that
moons? It has
many.
the most moons.
Jupiter has 95 moons. That's cool. So we only have one. I find again and again when you really begin to look at space science and our knowledge of space, our sense of reality begins to shift because the numbers are so big and so hard to get our minds around, but it's real. How did these 95 moons actually get created, and why are there so many? You don't have to answer that. I'm just having fun, thinking out loud with all of you. Okay, so Kishan, they say that 1.3 million Earths will fill the sun. 5 billion suns will fill the largest known star. Whoa. Kishan, who is they? Who's your source? Your Reddit? Oh, now I'm really nervous. Who on Reddit? That could have come out of somebody's head one night when they were having a few joints or a few drinks. Exactly. So who are they, Kishan? Exactly. I know. Okay. So let's forget about source for a moment and let's look at this. 1.3 million. I have heard it said about the size of Earth that many Earths could fit into the sun. That's how much bigger the sun is than Earth. I'm not sure that's accurate, Kishan, but it does tell us the beginning of something important, which is the sun is so much bigger than everything else in this solar system. And if you want to know more about it, the Parker Solar Probe is a really interesting program now that's traveling so close to the sun and is going to begin to provide more knowledge that we will have soon about the sun. Kishan, how hot is it at the center of the sun? Why don't you look that up and tell us in Celsius how hot it is? It's good you've been learning about quantum. Quantum is the cutting edge of science, and it's also something in medical science that's really important now, because if we can discover more about this, we can start to put things into the human body, human bloodstream, small devices, implants, like Elon Musk is doing with Neuralink, inserting implants into the brain to begin to help cure diseases or give humans more strength. But that's quantum technology, quantum science. Okay, great. So keep going, and then we will take this up in 2 minutes. Okay? Excellent. That's fine. Got 4 there, 5 over there, and Jake's just working on the 5th. So we're going to take this up in 1 minute, and then we will finish. Okay? That's good.
I'm going off vibes.
No problem, Lorelei. So let's see the average. Great. She's doing some good digging. And BBC. Okay, so when you're done, why don't you come back into the circle, okay? And we can all take it up together by reading off the board. And well, it's that time of day. If I had an espresso machine, I would have it going full power right now for everybody. But the best is to get up on your feet and start walking.
I already walk a lot. I have a dog. I call it a walker.
If you've ever spent time in airports and you get to that waiting for a plane and you're really tired and you can't sleep anymore, just start walking through the airport. That's what I like to do. Just walk and you'll get energy. Walking in airports, Jake, between flights.
I've been on flights. I'm not doing that. I get lost.
That is an experience that only humans have, not dogs, quite like humans or any other animals. Walking in airports to stay awake. Okay, guys, you don't have to come into the circle. You can do it from here. We're going to take up what is written on the board, a little bit of it, and then we're going to conclude. But first, I want to go to Lorelei and tell everybody about what she started with, okay? Because this is quite interesting. So here's some interesting information that will help you to begin to understand a little bit more about the scale. Opening ourselves up to cosmic scale. That's what we're doing in this class. And so here we go. Only 1 teaspoon of a neutron star weighs the same as the whole human population. So that's what Lorelei wrote in the live chat at the beginning. Only 1 teaspoon, neutron star. So then I asked her for a little bit more specific. So here's what she said. The average man, the average human, according to the BBC, or I believe that's the site she's working with. I won't challenge you too much on the sources now. This is good enough. The average man weighs about 70 kilograms. And the average for a woman is about 61 kilograms. So the average human would be around 65 kilograms. Fair enough. Okay, the average human is 65 kilograms. Multiplying 65 by the amount of people on Earth, which is over 8.2 billion, it would add up to approximately 5,300 billion. Okay, so that means 1 teaspoon of a neutron star weighs more than 5,330 billion kilograms. What is a neutron star? How can a teaspoon of a star, I can't quite get that in my mind, but let's try to. This is what Albert Einstein struggled with, but he finally got around to it. He said he dreamt of riding on a photon of light, that he had this dream, and he gradually could get his mind around traveling at the speed of light. Trying to do that in your imagination. It's not so easy. Light moves at 300 kilometers per second, a photon of light. Albert Einstein was dreaming of being on a photon of light like he's riding a horse. Can you actually imagine doing that?
Yes.
Can you, Jake? Because can you physically in your imagination begin to see yourself moving that fast? Or something moving that fast that goes around the circumference of the planet 7 times in 1 second.
Yes. I have a very active imagination.
That's great. Scientists are able to do this. They can open themselves to this big view. So then, here's the final question, and then maybe what I'm going to do, because I'd like to end it early, is we're going to leave this up here, and I'm going to save this, and I'll review it with everybody next week when everything's working properly. I want us to find out, what is a neutron star? The sun is a star. It's the center of our solar system. If we go into a new solar system, that's called what we know of that solar system is, I think it's Alpha Centauri or Proxima Centauri. That's the next solar system. Are those stars neutron stars?
A neutron star is
So what is a neutron star?
a celestial object of very small radius, typically 18 miles by 30 kilometers each.
with very high density coupled predominantly of closed packed neutrons. You just started the thought formed by gravitational class of remnant of a massive star of a supernova explosion, provided that the star is insufficiently massive.
Okay, I'll stop for a sec. It's tiny, but it's extremely dense.
Sun in a zip file.
What's that?
Sun in a zip file.
The sun in a zip file.
Yes. Yes.
That's lovely. Okay, this is cool. The sun, put the sun in a zip file, and you get a neutron star. So it's incredibly dense.
Big enough to form a planet, small enough to not cause a black hole.
Jake, this is a test of your imagination now. That tiny thing, the neutron star, weighs 5,330,000,000,000 kilograms.
What's that in pounds?
It's-
How much is that in pounds?
Oh, geez. I think I'm going to let you guys go. I just want to blow your minds with cosmic scale and get you opening to this new reality of space. Yes.
How much did you say it was?
According to Lorelei, a neutron star, one teaspoon of it, weighs more than all of humanity, all human beings on Earth. So she did the math. That's each human weighs 65 kilograms. She multiplied it by 8.2 billion, which is the number of people on the planet. She came up with the figure 5,330,000,000,000. So one teaspoon of it, a teaspoon, 5,330,000,000,000 and 30 billion. 5,330,000,000,000 kilograms is how much all humans weigh on this planet. Okay, I'm going to stop for a sec and just make sure we have everything here. Let's see if we can pick up one stunning piece of information. Okay, I'll read these out to you quickly so all of you know. What's that?
As Mjolnir. Horse hammer. Only the worthy can lift it. Otherwise, you can't move it at all.
Can't move it at all. That's
And I
nice.
also think I'm pretty sure I got it.
Good, Jake. You got your imagination really going. Okay,
It's a
so
very high number.
the star glows so bright that we still see them after they die out. That's nice. That's a star. That's called a supernova. Supernova is when a star dies. Good. Okay, now we got
Change it.
stars so bright that we still see them after they die out. We have so many sources of light in the whole universe, but it's still dark there. Excellent. Dark matter and dark energy, we are now beginning to understand, comprise most of what's out there, and we don't understand it. It's dark. It's dark matter, dark energy. So that's a whole large percentage of what's out in the universe. I can't give you the precise number that we don't understand. And you would have seen in the MIT video, dark matter, dark energy. So we have so many sources of light in the whole universe, but it's still dark out there. The whole universe and all the discoveries are just based on the smallest particle, which is quarks and that's right, quarks and this is the new ones that we've discovered.
LAPTONs.
Leptons. That's right. We've just discovered even more subatomic particles. We still don't have the exact smallest, but we used to have just protons, neutrons, and electrons. Then we figured out there are particles inside of those, and then there's particles inside of those, and we get smaller and smaller. And then electrons. The sun is so big, it can fit all the planets in it, absolutely. Staying space. What's that? You have to staying space?
Staying in space for a long period of time causes our bodies to stretch out. Curing, in quotations, things like scoliosis. So prolonged exposure will cause health problems when returning to Earth.
Okay, let's end with this fact, because I think this is really if we're in space for a long period, our bodies stretch out?
It's because we're no longer weighed down by gravity. So we start expanding more.
Where does that come from, that fact?
Lack of gravity, I guess. I don't know.
I would like to know if that's true.
Yeah,
Is it? Because that's fact. We stretch out because of
And
Less gravity?
There's been scientific documentations of astronauts
If
and
it's not gravity,
like
then
Neil
we are just
Armstrong
stretching
and
out.
the
We are
sort
just going longer.
due to spending so long in space stations and all that, they physically grew. Like their body expanded, but the moment they got back on the Earth, it caused health problems. They weren't able to walk as well, and their bodies started to compress again because they're being grounded by the
Yeah,
gravity,
sure. I understand the general.
causing their ligaments to again squash more, their muscles to condense.
Can I say something?
There's even a movie
Fascinating.
about I think a boy born on what happened if someone was born on Mars,
Yes.
where literally his heart and lungs were so big that he could not leave Mars. If he went on Earth, the difference in gravity would really
Would crush it. And how long, do we know how long it would take for the crushing to happen? Would it be fast or slow?
I think it's a mix. I can't exactly remember. 'Cause I can't remember much about the movie.
Yeah.
But I think for someone like that was born in space, it would be quick. But for somebody who was in space but was originally on Earth, it would be slower because your body's just basically returning to where it was.
Well, it makes a lot of sense because here's one fact we know of that's very common. Do you know when astronauts come back from the International Space Station or from any mission, even for a few weeks, they all suffer from a mild to less mild form of depression. Did you know that? And you know why? When you're in a gravity-free environment, you're much lighter. When you come back to Earth, everything is heavier. You're being pulled down to the earth. You have to, and you feel more sluggish. And so that is a mental thing too, because the mind feels like has a sort of a weight on it too, because gravity is pulling you to the earth at that point, and that feels like weight. And that can be mentally difficult for astronauts. But they know that when they come back to Earth, that they're going to experience this. We will be dealing with these kinds of things more and more in the next 100, 200 years. Humans having to adapt. How do we deal with that? You final thing, and then we're going to stop, okay? You wanted to mention something? You're good? Okay. I want to let you all go 10 minutes early so you can get things done, and I can most importantly get a handle on the tech issues we've been having. And so look at this. Lorelei has finally here we are. Thanks, Lorelei. I didn't have this completely scrolled down. She had answered, what is a neutron star? And they're formed when a massive star runs out of fuel and collapses. This crushes every proton and electron together, creating a neutron. Thank you, Lorelei, for that crushing piece of insight. A neutron star is this tiny thing because it was crushed. All of its subatomic particles, at least proton and electron, right, are crushed together, creating a neutron. Okay, so discussion post 9 is due next week, and I should have everything fixed hopefully then. Does anyone have any questions before I let you go? I'm going to save this, and we will review this next week. Are humans going to be evolving, or what will they evolve into?
Because you said we'll start adapting over the course of 100 to 200 years, right? So
We have been since.
And that idea, humans will start evolving again, and we as humans have been so stagnant.
Yes.
For so many years with at least our appearance and our bodies.
Yes.
The only difference changing is the diseases we can now take and can't take. So will this cause us to be larger? Will it cause us to be smaller? Will it change our density, or will it change our appearance?
I'm going to tell you, I think you just have the content for your final assignment in this course.
I like thinking.
Those questions you asked, well, write them down, Jake, as soon as you can, because I think that your attempt to answer those questions with science could be your final assignment.
Can I use video games?
What's that?
Can I use video games?
Yes, you could.
Hell yeah.
Absolutely.
That means I get to go play Mass Effect.
Charles Darwin, who gave us evolution and told us what evolution said, humans have been evolving, of course, and we will continue to. The question is, what will we look like? Andrew, thanks. Okay, guys. Yeah.
Like two
You-
questions you asked me. to
Yes,
write down.
thanks a lot. I'm gonna save everything now, okay? And get it posted for everybody. Thank you, everybody in Lorelei, for your good digging, and I'll see you all next week, hopefully with all.
Bye.
Take care. Okay, I'm gonna save.
Bye.
I have to save the recording. I don't want to make this mistake.
Have a good week,
Yeah, thanks.
Mr. Appleby.
Take care. Okay,
Bye bye.
bye-bye.
I hope I can see you in person next week.
Well, if not, you always can join this way, Manish. No problem.
Have a good weekend.
Take care. Okay, here we go. So save the recording. This is critical. Stop the recording. Great.